Howdy Cal folks, Mr. Norman here. We're going to be going over our first lecture for the school year. We're starting in our online textbook, lesson 1.1. So I'm going to be going in a slightly different order than what the page has. I'm going to talk about the real numbers. You may or may not remember this from your other classes. So we're going to go over the natural numbers, the whole numbers, the integers, the rational numbers, and the real numbers. All numbers that you can think about are real numbers. There's one type of number that's not, it's complex numbers. So there it is. We're going to go to Google. Here are examples of each. So we have the natural numbers, the counting numbers. That's the whole numbers, not including zero. So if you're going to count how many somethings you have, 1, 2, 3. So how many circles are here? 1, 2, 3. Notice we didn't start at 0. So the natural numbers, aka the counting numbers, don't start with 0. Then we have whole numbers, the natural numbers, plus 0. Integers, it's just the number line. Negative numbers, positive numbers, 0. They're all whole numbers. So the next part is where things can get a little confusing. Rational numbers. The way I think about rational numbers, it's an integer. If you can write it as an integer divided by an integer equals a rational number. Another way to think about rational numbers are that they're ratios, which means a number divided by a number. So any integer that we can think of can be on top, divided by any integer that's not 0. Don't divide by 0. You don't want to kill the dinosaurs. That's how you kill the dinosaurs. So 1/3 is a rational number. Oh, wait, no, that's not the symbol for rational numbers. Rational numbers are Q's. A fancy Q. So even though 0.3333 is a repeating decimal, we can write it as a ratio of two integers. Then we have irrational numbers, which basically means we cannot write them as a fraction. We can't write pi as a fraction. No, 22 divided by 7 is not actually equal to pi. It's an approximation. They're not the same number. We have e, we have the square root of 2, and we have this long decimal that's not going to have a pattern. Later on, at your request, I can make a video explaining why the square root of 2 is not a rational number. It's actually one of my favorite things to do. It's pretty fun and incorporates Pythagorean theorem. So I'll put the note here. Let me know if you want square root of 2 proof. And I can provide it. It's not a TEK, so it's not required. So these are all the numbers. The reason why I covered that first is because we're going to be talking about sets. Sets are a collection of things. You can have a set of numbers, you can have a set of keys, you can have a set of cups, you can have a set of video games. Like I do have a set of all 2Ks. Okay, not all the 2Ks, but pretty dang close. So we have a collection of objects. So we write a collection of objects in a set of parentheses. Curly braces. I'm terrible at writing these. So this is a set of numbers. So I'm going to write a set. And we know it's a set because of these two parts. So this is a set. We also have a thing called a subset. A subset is just a smaller version of a set. So we have this subset. If we have 1, 2, 3, 4, 5, we can have 1 and 2. Or 1, 2, 3, 4. Or in the empty set. All of these are subsets of that set. I better write that. This is called the empty set because there's nothing in it. Very complicated, I know, but I have faith you can figure it out. So these are all subsets of green set. We can even have a subset of the numbers. If you look, we have the real numbers, and all the things inside of here are subsets of that. So we have the big set, real numbers. Then we have two subsets of that. So ignoring the irrational numbers, the real numbers, the rational numbers are a subset of the real numbers, and the integers are a subset of the rational numbers, and the whole numbers are a subset of the integers, and the natural numbers are the subset of the whole numbers. And then 1 is a subset of the natural numbers. So now we're going to talk about intervals. So we have bounded intervals. That means they have an endpoint, which basically means you don't go to infinity. So any bounded interval has a finite length, which means you don't go to infinity. So these are really straightforward. We have an inequality. A is less than or equal to x, which is less than or equal to b. Another way of saying it is x is between a and b. The line means inclusive. The block shows you that it's equal to. Line here, line there. So the way we graph this, A to B, with a solid dot to show that they're equal. So bar underneath means equal. So does the square bracket. So does the closed dot. Here we have an open interval because we do not have equal signs. So x is between a and b, not inclusive. Oh, parentheses, same thing as not equal to. Open circles, the same thing. Here we have a mix. Line, square, closed circle. No line, parenthesis, open circle. No line, parenthesis, open circle. A line, square, bracket, closed circle. So, as this note says, the length of any bounded interval is the distance between the points. So you just subtract the last from the first to figure out how long it is, which sounds strange, but it's actually what we do in number lines all the time. So if you're like me and sometimes you need to write a number line to do your integers. So if I start at -1 and I add 1, how far did I go? I went a distance of 1. So if we do like the book said, this is it. Sorry, this is A, B. So B minus A equals distance. So 0 minus a -1 equals 1. Remember, do this. Minus negative turns into add. So we have a distance of 1, just as we'd expect. Unbounded interval just means there's an arrow, it goes on forever. And in case you need a refresher, this symbol means infinity, this symbol means negative infinity, and again, infinities means it's unbounded. So here we're going to go through the example. So write each interval in interval notation. Reminder, interval notation is this right here. So we'll work the example. So here we have a bracket. We have a line, so we'll have a bracket. Here we have another line. We'll have a bracket. So -2 to 3 is our interval. Here we have no bracket. X is greater than -1. So we have -1, and X is going to be bigger. So does it say how big? It doesn't stop, which means it's unbounded. Since this has no equal to, it's a parenthesis. Nothing can equal infinity, another parenthesis. So for C, we have to read this. This closed circle means bracket. This open circle means parenthesis. This says -3, comma. This says 4. This keeps going and it doesn't stop. We're going to go all the way to negative infinity. Can't actually equal it, so we'll have an open bracket. Here we have a closed bracket. Sorry, we have a closed dot, which means we have a bracket. The number is 3. And if we go back, it has the same answers as we put. Monitoring progress. It's your turn. Make sure you write this down inside of your journal. And after a jump cut, you will see your answer. So here are our answers. I hope that makes sense to you. If you have any questions or need some help, you can email me at anorman@isd.org. You can also communicate with me via Google Classroom and through Remind. Next, we will discuss set builder notation. It looks complicated, but it's really not. So as it says, set builder notation uses symbols to define a set in terms of the properties of the members of the set. Do what now? It's really straightforward. The set builder notation explains to you what is occurring. So open parenthesis, close parenthesis. This just lets you know that this is a set. This just lets you know it's a set of all real numbers. So X represents all real numbers, which also means any real number, such that, this line means such that X, our numbers, are less than B. So for this graph, the set, curly brackets, of numbers such that those numbers are less than or equal to A, or those numbers are bigger than B. Not inclusive. And this is what the graph looks like. So once again, another example, curly braces, a set of numbers such that those numbers do not equal X. So again, this just means, oh, that's not a good color. These just mean a set. This part just means of numbers green such that, not tat, that those numbers something. So set builder notation. Reads a set of numbers where those numbers something. Or, to save time, x such that x. And trust me, when you get into some college level math classes, this saves you so much time. So here we have an example. Again, a set of numbers where those numbers are between 2 and 5. Not include, no curly brace, parenthesis, square bracket. Again, the real numbers in a set satisfy both. This is what they're saying it means, but it's math talk. We're going to simplify it. Yes, numbers where they are between 2 and 5. Here's the graph. Once again, here we go. Numbers where x is less than or equal to 0, or x is bigger than 4. X is less than or equal to 0, equal to because of the closed dot, or the numbers are greater than, not included, than 4. Oops, that was not supposed to happen. On to example 3. Write a set of numbers in set builder notation. So we need a set, so we have curly braces, of numbers where those numbers are greater than 5. They also have to be integers. Since it's the and, we also could have written it the other way. Where set of all integers where they are greater than 5. So again, we have a set of numbers where those numbers are integers. Do you have to teach all a new symbol? Yes. This symbol means an element of or belongs to. It just means x is a integer and x is greater than or equal to 5. You could write it either way because and goes both directions. X can be any real number except -1. So there's a set where x is not equal to -1. So here's a modern progress. These 4 are for you to work on. Please make sure you're following along inside of your composition book. And after the jump cut, you'll have your answers. Here are your answers. If you have any questions, please contact me at anorman@ednaisd.org. You can also contact me via Google Classroom and through Remind. This is the end of the section. Thank you for being such a good trooper. I will have practice problems to pair along with this. Have a good day. Peace.